Welcome back everyone to coding part 2 for hierarchical clustering. In part 1 we went through the visualization aspects of clustering with Seaborn and being able to see the dendrogram there. Now we're going to switch gears to focus on using scikit-learn. And we're also going to explore how we can have two methodologies. One is to choose the number of clusters beforehand, and then the second one is to try to use that dendrogram and just the distance threshold in order to have the scikit-learn algorithm help guide you into choosing the best number of clusters. Let's get started and head over to the notebook. Okay, here we are at the notebook where we left off last time with the visualizations. What we're going to do now is use scikit-learn to actually perform the clustering and get the labels themselves. So keep in mind that for scikit-learn, hierarchical clustering doesn't fall under some sort of code of hierarchy clustering or hierarchical clustering. It's actually in the code itself as agglomerative clustering. So keep that in mind. And then the hyperparameters we're going to be exploring is whether or not you define the number of clusters beforehand, sort of a k-means approach, or if you end up using something like the distance threshold in order to have it guide you to choosing the correct number of clusters. So let's explore this. I'm going to start off by stating the fact as if we knew how many clusters we wanted to have to begin with. And you could always use a visualization to help guide you. So you can see here there's two major clusters between US cars and non-US cars, but maybe we're really just focused on trying to find these four clusters here. So what we can do is begin by saying from sklearn.cluster import agglomerative clustering, and then create a model. And right now, for this model, what I'm going to say is number of clusters is equal to 4. Okay. And then recall that we have the scaled version of our data frame. And the scaled version of our data frame uses min-max scaling, so the lowest possible value is 0, and the highest possible value is 1. So something to keep in mind, that we have this scaled version of our data, and to get the cluster labels, it's pretty simple. We're just simply going to say cluster labels is equal to model fit predict, and then we have just pass in scaled df. Again, no need to do any sort of train test split because this is unsupervised learning. There's no correct answer to compare it to. It's not like these cars already have some sort of class label to them. So we run this. Notice it runs really fast on this data set. Then we're going to say cluster labels. And here you have it based off index position, the actual labels of the clusters. We said n clusters is equal to 4, meaning there's 4 potential clusters, cluster 0, 1, 2, and then 3. So how can we actually use this? If you want, you can visualize this against features or multiple features based off the cluster labels. So what we could do is something like this. I could say sns.scatterplot, where my data is equal to my original data frame, which holds the same index positions as my scaled data frame, and then say x is equal to miles per gallon, for example, and then say y is equal to weight. And if you just run this, you should get something that looks like this. As your weight decreases, your miles per gallon will increase. And what we can also do is make this slightly larger so it looks a little nicer. PLT figure, and then say fig size is equal to 12 by 4, for example. Let's make the DPI a little sharper as well. And we would have been able to do this without the clustering. But we do have these cluster labels, which means I can now add them in as a queue, cluster labels, and begin to visualize what these clusters are actually representing. Of course, cluster interpretation is always the hardest part of unsupervised learning when it comes to clustering because there is no correct answer to compare this to, but we can see what the algorithm in general is doing. So it looks like everything's being stratified based off kind of efficiency of the car's ability to actually run or have miles per gallon versus the weight of the car. So we see here one category for very heavy cars that have low miles per gallon, and then it looks like this darker number 3 is starting to trend towards lower weight cars that have higher miles per gallon. And you can begin to compare things also like horsepower against these few clusters, for example, horsepower here, and begin to try to understand what is separating out the clusters. And clearly we have this one cluster, this kind of pink, and you can always change the color mapping here. We can say something like palette is equal to this, if that's easier for you to see. And here we can see this clearly, this blue cluster are the high horsepower, low mile per gallon cars. And then here, these other 3 clusters seem to be kind of in the similar range of horsepower and miles per gallon. This is where you want to start comparing other features, or maybe you just want to say, hey, let me come back and change my number of clusters, such as maybe 3 clusters or 2 clusters, rerun all this, and then begin exploring the differences there. And you can see once I've gone down to 3 clusters, I no longer have that separation of this horsepower versus miles per gallon, because this 0 cluster goes all the way to kind of over here where we have high miles per gallon and low horsepower. So something to keep in mind. Okay, so this is nothing new to us. If you had an intuition of how many clusters to choose, this is no big deal. You would just run this and then begin exploring. Main problem here is we wouldn't really need to explore too much visually if we already had a good intuition on the number of clusters we were expecting. So instead, we want to really take advantage of the fact that we have the dendrograms to work with. All right, so the first thing to understand as we're going to move to not having to choose the clusters beforehand is come back to the actual documentation and realize that there is this affinity hyperparameter, which is essentially just what distance metric are you using to compute that linkage between a point and a cluster. So you can do something like the default Euclidean, but also note there's the Manhattan distance, cosine distance, etc. I would highly recommend that you just use the default Euclidean because it's going to be really easy to understand in conjunction with the min-max scaling. So if we take a look at Euclidean distance on Wikipedia, it's essentially just the Pythagorean theorem. So what is the distance between this point and this point? Well, it's a squared plus b squared is equal to c squared. And notice here that the distance squared is equal to the differences on feature 1 squared plus the differences on feature 2 squared. So we have 2 points here. Let me go ahead and click on this diagram, make it a little larger. We have, again, 2 points here, point P and point Q. And then we can imagine that we have feature 1 and feature 2. What's really nice about min-max scaling is you can immediately understand what the max possible distance could be, because you know the lowest possible value is 0 and the max possible value is 1, meaning each of these at most would be 1. So you would have, for example, 1 minus 0, the max possible distance between the feature 1 point squared, which is 1 squared is 1. And then you could have feature 2, again, max possible distance is 1, and 1 squared is 1. So then you have distance squared is equal to 1 plus 1, essentially saying that the distance would be square root of the number of features, which is perfect for us. So that means if we come back to our notebook and we try to answer the question, what is the max distance possible? Then we know it's actually going to be equal to the square root of the number of features. Okay. So how many features do we actually have? Well, it's simply the length of the columns in our data set. So for training on scale df, length of the columns there is 10, meaning if I take np square root of 10, essentially the max distance, so this is the max distance possible between 2 points in our min-max scaled feature space. And it's going to be 3.16. So keep that in mind and review Euclidean distance here in case this is still confusing to you. But again, this is due to the fact that we did that min-max scaling, which is why we specifically chose that particular method of scaling, because that way the max possible distance on all the features would be 1 minus 0 or 1 squared, which is 1, meaning when you sum all those up, you would get the number of features, but then to get the distance, because it's a squared plus b squared is equal to c squared, then we would have to take the square root of that to get the actual distance itself. In this case, with 10 features, max possible distance between 2 points is 3.16. So how do we use this information? Well, we come back to the scikit-learn class, and then we'll realize that there's this interesting distance threshold argument that by default is none, because by default n clusters is 2. But you'll notice it says here, it must be none if distance threshold is not none. So let's start by setting n clusters to none. So we come back up here, I'm going to create a new model. So the way we're going to do this is say model is equal to agglomerative clustering, and then say n clusters is equal to none. But that means I now have to define a distance threshold. So we come back up here and try to understand what distance threshold is. Well, it's just the linkage distance threshold above which clusters will not be merged. So what would be the kind of absolute minimum here? We could think that if I set the distance threshold to 0, that means that nothing is ever going to be merged. So 2 points are never going to be merged because the distance threshold between them is 0. So they can be essentially 0 units apart, and we're still not going to merge them together. Let's see what that looks like and see if it matches up with what we intuitively think would happen. If I set the distance threshold equal to 0, recall that the max distance possible between 2 points, right now for this particular case, is 3.16, but I'm going to say even if there's 0 distance between 2 points, I'm still not going to join them together to the same cluster. Which means if I have this model where I'm not saying the number of clusters, instead I'm saying some sort of distance threshold before we start joining them. In this case, I've gone to the extreme of 0, meaning 2 points, 0 distance between them. I'm still not going to join them together. Then we're going to say cluster labels is equal to model fit predict, and let's pass in our scaled df. Okay, so take a second here and see if you truly understand what's happening and what do you intuitively expect these cluster labels to look like. Keep in mind that the distance threshold equals 0, and distance threshold is the linkage distance threshold above which clusters will not be merged. So I would expect cluster labels to essentially assign a unique cluster to every single point, which if you take a look at it now, is exactly what you have. Notice you have essentially a cluster label that is unique to every single point here. So we have 0, 1, 2, 3, 4, 5, etc. So what's actually happening here is because I set the distance threshold equal to 0, that's essentially the maximum number of clusters possible. And you can think about this as if you were using k-means and decided that you're going to keep increasing k until you get to the number of points. It's analogous to that. So we have these cluster labels here. What we could do is kind of build off this linkage model to build a dendrogram, but let's just explore what would happen if we kind of went the extreme way and said every single point is its own cluster. Well, luckily for us, SciPy has some capabilities here. We're going to say from scipy.cluster.hierarchy import dendrogram. And this is a visualization function that will automatically visualize the dendrogram for us if you give it a linkage matrix. So we also have to say from scipy.cluster import hierarchy. Okay, the other thing you could do is say from scipy.cluster.hierarchy import linkage, but either way is okay. We're going to create a linkage model or a linkage matrix. And you can come to the SciPy documentation, check out scipy.cluster hierarchy dendrogram, and get an understanding of what this is talking about and what this is showing. But really, it's just going to be a matrix showing the two clusters, the distance between them, and then their closest other cluster assignment. Which means I can say linkage matrix is equal to, I'm going to call hierarchy linkage. I could have also just said from scipy.cluster.hierarchy import linkage. Either way is okay. And then we're going to pass in the model children underscore. So when you run that, whoops, make sure we do this correctly. There we go. When you run that, you're going to get a matrix. And it's going to look something like this. All right, so what do these numbers actually represent? You can go to the hierarchy linkage documentation page from SciPy. So I have that open here, and the full explanation is right here. It's a little mathy in its explanation, so I'm going to kind of summarize what this explanation is here, but you can always just check out the documentation page for scipy.cluster.hierarchy.linkage to fully understand what this matrix is actually returning in full detail. But I'll explain the general concept. So we have this linkage matrix. What it's representing here is an index 0, that is column 0, and column 1. It's essentially saying that we're going to combine these 2 points, or these 2 clusters really, in order to form a new cluster. So the third point here is the distance between cluster 67 and cluster 161. So what does that actually mean? In our particular case, because we said distance threshold is equal to 0, then we can directly compare these clusters. So I know here that cluster 67 is essentially the 1.67 somewhere in this matrix. It's actually right here. And then we have cluster 161, which is some point kind of around here somewhere. Okay, so that means that I have this point aka cluster number 67, and this point, aka cluster 161, and then I have the distance between them, and then I also have the actual number of points in this particular cluster. And so what's happening here in the dendrogram, as you go higher and higher up, you're going to have more and more points in the cluster until everything falls under that first split that's happening in the dendrogram. So we have this particular cluster point, this particular cluster point, the distance between those, and then we have how many points are in that cluster. So it starts off small, essentially at the very bottom of the dendrogram, and then it starts off or ends all the way at the top at 391, which you'll notice is essentially n minus 1 points. Okay, so what do we actually do with this matrix? This is essentially the mathematical information that is used to actually plot out the dendrogram. So we're going to do that right now. Keep in mind, this plot can take a while to run, especially if a large data set. It may crash. So we're going to say PLT figure, say fig size is equal to, I'm just going to make this large, let's say 20 by 10. You can play around with DPI as well. And then I'm going to say, for example, dendrogram or dendro is equal to hierarchy dot dendrogram. And I believe I actually already imported this. So you could have just called dendrogram here. So let's just call it here. Dendrogram. And then you pass in that linkage matrix. So SciPy is going to use the linkage matrix here in order to actually visualize what this information is. So you can essentially think of this as these are the 2 points it's going to show on the x-axis. This is how high it's going to make the y-axis bar, and then this is how many points it's actually connecting in total underneath it. So that's why we get something that looks like this. And if you were to zoom in really closely, you would notice each of these numbers is essentially a unique number per data point or per car in our data set, which corresponds with these actual cluster points here. So you'll notice we have a bunch of tiny little 2-car connections, so to speak, and that's what starts off your linkage matrix. So we have 67 and 161, and those 2 points are connected. So somewhere along this x-axis, you would see 67 and 161 connected by these kind of hierarchy dendrograms. And then the height of it would be 1.41. That's the distance itself. And you can see as you get to the very top, this is kind of the top right here, what's actually happening here is you have these large clusters, cluster 349 and 779. So notice just how much larger this cluster is, 779. That's not going to be up here because now that's a cluster that is kind of combining a bunch of other clusters underneath it. And that's going to have a distance metric of 75 between them, which is why it's the very top one here. You'll notice 75 is the very top. That's why it kind of starts here at 75. And then there's 391 points underneath it. And that's what this linkage matrix is representing. It's the 2 clusters, it's joining together, the distance between those 2 clusters, and then the number of points falling in for this particular linkage or connection. So you would always expect it to start off at 2 because that's essentially the absolute minimum number of points you can connect, and then you would expect it to eventually end at n minus 1 number of points in your data set. And as you continue to go on, this cluster number, which is essentially just kind of an index tracking how many clusters you've been creating, essentially how many of these links are there throughout the entire dendrogram, you would expect that to get higher and higher. Okay, so is this particularly useful? Yes and no. It's not super useful to see here at the very bottom every single individual car. What is useful here is you begin to start making some sort of judgment call on where you should kind of cut off this hierarchy. So one way to do that, just visually, is by taking advantage of the SciPy visualization technique with a truncation mode. And if you come back to SciPy cluster.dendrogram, you'll notice there is a truncation mode called truncate mode parameter. So the parameter here is truncate mode, and you can call last p or level. It's up to you however you want to think about it, but it essentially is something you can add in. So you can say last p and then add in a p hyperparameter, which is going to kind of prematurely cut off that dendrogram. So easiest way to understand it is to just play around with it. So we can come back up here. You can also say level, and then no more than p levels of the dendrogram are displayed. So you come back here, and underneath dendrogram, I can say truncate mode, And for example, I can say last p, and then choose some p number like 48. Actually, let's make it just really obvious. I'm going to say p is equal to 10 here on last p. So you run that, and you've truncated this, and you notice you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is last p, which is based off on just these links themselves. Now, something to understand here, as you begin to truncate, you're not really able to interpret this x-axis so nicely anymore, because this is just referring to the cluster numbers it was giving before, which is no longer linked to what you have here in scikit-learn. So just keep that in mind. If you see something like 779 here, it's not going to be completely useful for you right here. So the x-axis, not super interpretable or easy. Again, we're really just using this to kind of help us decide how many clusters should we choose if we were to go back and instead of using distance threshold, come back and then begin defining it by n number of clusters instead. That's really what you would use this visualization for. The other truncation method we knew of was called level, or levels. Let's actually review that right here. Level, and then it's no more than p levels are displayed. So for example, now if I said p levels is equal to 3, run that. Notice now I just have 3 levels. So here's level 1, level 2, and then level 3. You can kind of think of it as how many of these kind of T-bar connections do I have. Here's level 1, level 2, and level 3. And this would actually then help you kind of more directly choose number of clusters. Okay, so those are your 2 truncation modes available in order to guide you and understand what is a reasonable understanding here for my linkage matrix and my dendrogram. Now, as far as coloring is concerned, this is another way SciPy tries to help you out. This one's a little more complicated to understand, especially as having it guide you, but there is a color threshold you can use, which is essentially just defining the cluster nodes and how you're going to color them. And then I would just recommend using the default. It's not super useful in trying to decide the number of clusters, but it is another tool available to you, just like truncation. But I would, in general, not recommend being completely beholden to this idea of trying to use the visualization, especially for super large data sets. It's going to take a while before you can kind of easily truncate, and you have to keep guessing at this truncation level until you feel something or see something that you're comfortable with. Instead, what we're going to do is see if we can choose a threshold distance by truly understanding that Euclidean distance, which means if I take a look back at my scale data frame, recall that my max values, in fact, let's just say describe here. As I keep mentioning, my max values are 1 and all my minimum values are 0. So that means my Euclidean distance, the max possible distance, is np dot square root number of features, which is going to be the length of scaled DF columns. Because that means we would have one particular car that in theory would have 1 mpg, 1 cylinder, 1 displacement, 1 horsepower, etc. And then on the other end of the spectrum, we have another car that has 0 mpg, 0 cylinders, 0 displacement, 0 horsepower. Now, does that car actually exist in the data set? Probably not. That would mean you have 1 super minimum car and 1 super maximum car. But it is helpful for the theoretical max distance. So if you run this, as we mentioned before, this is our theoretical max distance. Now, what's a realistic max distance for the cars we actually have in our data set? That's easy to do. We can just choose an important feature like miles per gallon, mpg, whoops, make sure that's a string, mpg, and then find the max value here. So the max mpg value is actually 1 as we expect, and let's find its index position, idx max. So car at index 320 has the highest miles per gallon. Let's find the idx min. Car at index 28 has the minimum miles per gallon. So we have this car, very efficient, very high miles per gallon, and then the most inefficient car, lowest miles per gallon. And this is essentially, we come back to our scatter plot. It should be essentially this car right here with super low miles per gallon, and then this car over here with very high miles per gallon. And what we're trying to think of is, we know the maximum distance between 2 points is the square root of 10. But realistically in our data set, what's the distance between the lowest miles per gallon car and the highest miles per gallon car after we've min-max scaled everything? To do that, we can use the linear algebra with scikit-learn, which is going to automatically calculate that Euclidean distance for us. So we can say A, or car A, let's say that, car A is equal to scaled df ILOC 320, and then car B is equal to scaled df ILOC 28. And what's the distance between them? The Euclidean distance, that's simply equal to NP linear algebra norm car A minus car B. Okay, so the distance here is 2.38, which means I know my theoretical max is 3.16, but realistically, between the two cars, the one that has the most miles per gallon and the least miles per gallon, which we saw is quite a heavy differentiator between these general cars, that distance is 2.38. Now, something to keep in mind is this is technically just the theoretical distance between 2 points, not the distance between two clusters. And you can come back up here and review your linkage matrix for the actual distances between two clusters. This is all to say that these are just starting points for you to begin exploring. You'll notice that kind of this minimum threshold is over at 1.41. So understanding the distance between these two cars at 2.38 starts to give you a reasonable idea of maybe where you should start adjusting your actual distance thresholds. And this is the max theoretical distance between 2 points. Keep in mind, max theoretical distance between 2 points is not exactly the same as the max theoretical distance between two clusters of multiple points. So just keep that in mind. It's not like if you were to put 4, suddenly everything would be put into the same cluster. You can see those distance metrics right here. Okay, so that's all to say that this is just a jumping off or starting point, and we know that there's kind of this minimum distance of 1.41, and then we have this kind of extreme difference of 2.38 between these two cars, this max distance between 2 points at 3. So it's probably a good idea to start around 2 or 3 to begin your distance threshold. So we'll come back up here. Let's go ahead and put in 2. Run that. And here you can begin to see how things are clustering out. And we can see the cluster labels. And you can see it's essentially made 11 clusters. So you can come back up here, review the linkage matrix. It should be the same every time, but really what you're affecting is where you're cutting it off. So you can say, hey, P is equal to 11 clusters, and my truncate mode is now equal to last P. And this is going to essentially reflect where you decided to cut off your clusters. So again, this is very exploratory, and it's always up to you to decide what these clusters actually represent. But understanding that Euclidean distance metric is going to help you, along with the dendrogram, decide where's a good cutting off point for my particular number of clusters. And of course, you could, instead of using that distance threshold, once you start getting an understanding or an idea, come back and start setting the number of clusters directly instead. A lot of this, as we always keep saying for unsupervised, it's very exploratory, very nuanced. These are just starting points for you to begin exploring what values for hyperparameters you should begin putting into your models. Okay, thanks, and I'll see you at the next lecture.